last talk of the day by Zi-Wen. It's going to tell us about various results on convergence efficiency of quantum gates and circuits.
Thanks. Yeah, first of all, thanks to the organizers for making this happen. Today, I will tell you some recent progress on convergence or design generation efficiency of quantum gates and circuits. Those results are mainly contained in these two papers with these three wonderful junior colleagues. So I decided on this topic because I find it aligned the best with the title of the workshop conference. But let me spend a few minutes briefly introducing some other very recent works that might be of interest to some of you. So the number one and number four are about doing logical gates, encoded logical gates on quantum error correcting codes. So the first one is targeted at understanding the fundamental restrictions as well as constructions on doing logical gates with product-based quantum LDPC code. So this paper we have delayed for a long time, but hopefully we'll post the number one of the series of papers soon, and there will be some other ones upcoming. And number four is about a slightly different notion of logical gates. Here we define continuous variable quantum codes on triangle tessellations on 2D surfaces with different curvatures. And the amazing thing is that so we show this provides us with a very interesting geometric formalism for doing logic gates. What I mean by that is we can tune the tessellation and the curvature of the surfaces to do versatile logical gates by geometric rotations on the surfaces. And number two is very closely related to the extremely shallow circuit talk that we heard this morning. It's sort of relevant, but slightly different. Another side of the story, like we focused more on the information theoretic perspective of these very shallow log depth circuits. We show some new decoupling theorems of these shallow circuits, which gives us conclusions about very ideal approximate quantum error correcting and capacity achieving abilities of these circuits. So yeah, this is also relevant to the talk this morning. And number three is here we introduce the theory of long-range non-stabilizerness or magic. And in my own words, I will describe it as a strengthening of the long-range entanglement theory that we are very familiar with for both physics and computational complexity reasons. Because so here by defining the theory about magic, we are sort of unifying the classical basis of these theories. We are including these classically computationally efficient stabilizer states, as well as the short-range entangled states. So it's like sort of a more unified theory about non-classicality, which has some computational underpinnings. And in that paper, we also discuss about the very interesting connections with a bunch of different things, including quantum error correction. And in physics, this goes towards a grand goal of mine of trying to understand or use the computational complexity boundary to define a new notion of phases of matter. And also this has some insights for things like quantum PCB, which is within the realm of computational complexity theory. And then the last one is I'll describe it as a space-time framework for a unified space-time framework for circuit complexity that also covers the measurement-assisted preparation that I think many of you are interested in, and this framework is very relevant to a bunch of things, including deep thermalization, shadow estimation, holography, random circuit sampling. For these topics, I see a lot of pioneers and experts in the audience. So yeah, so these are some of the other works that might be of interest to you, and I'll be happy to chat about them too. And for this talk, so this is the outline. So first of all, this talk will be a bit more on the mathematical side of the random circuit story, and I look forward to learning more about the physical perspectives from you guys. And so first, the central element of the work is a quantum circuit model and the design generation or convergence problem. We've heard about some definitions in the morning, so hopefully I can be a little faster with the background. And then, so we will talk about this problem in two different frameworks. The first is what I call the stochastic quantum circuit framework, where basically instead of hard random local gates, we allow some arbitrary ensembles, and we consider the convergence properties of them. And then for the second framework, we talk about these local circuits under continuous symmetries. So in the morning, we have heard some story about how the discrete symmetries are phi. But here, let's see something about why continuous symmetries are poses very fundamental difficulties on this problem. And I think the content of the slides is probably too much for 1 hour. So at least I hope to explain as best as possible this iron circuit model that I personally find to be very interesting. And if I don't have much time left, I will just try to skim through the rest of the results relatively quickly. Okay, so our basic playground is this local quantum circuit model. So as we all know, so this circuit model, what I mean by that, so they're composed of local quantum gates, sometimes with geometric constraints, sometimes not. And we are usually concerned or interested in how they compose some global unitary or property. So we know that this is the natural language for implementation of quantum computing, and it also characterizes circuit complexity and stuff. So it's it's a basic model for quantum computing. And in recent years, it also has gained a lot of emerging interest in physics as a versatile model for complex many-body quantum dynamics. That should be the theme of this conference. So let's explain the pseudo-randomness at this high level. We already see that. So here the critical notion is T design that we heard about in the morning. So T designs. Let me repeat it. We say it's a statistically pseudo-random ensemble as opposed to those computationally pseudo-random ensemble, which means that this is also a distribution, but it's not necessarily uniform, but it matches the uniform Haar measure up to T moments that we call them T designs. And this contrast we also saw. If we want to prepare a Haar measure, it requires exponential depths But for T designs, it's possible that it's possible to prepare them with lower complexity. And this T design regime is already sufficient or relevant for a lot of applications and physical phenomena. Okay, so let's look a little bit into how local random circuits, the basic phenomena that local random circuits, uh, local how global randomness emerged from local random circuits. So this is one layer, and as we do deeper and deeper random circuits, some properties like entanglement and OTOC will, well, some reverse version of OTOC will grow. And also, if we look at, so this circle represents the unitary or state space. And what happens is we explore more and more of this space. And at some point, it will look somewhat uniform. And these some basic properties like entanglement and OTOC will saturate. So this roughly happens at this two at the two design point, and there are some. You can also define some higher order properties that will keep growing. And if you look at things like circuit complexity, it will grow for much longer, exponentially long time until you reach the Haar measure. But this two design is a point where some basic properties will already saturate, and yeah.
Randomness kick in before it becomes before entanglement, is that true?
Uh, yeah, you're right. So this is a little tricky. Yeah. Okay. So yeah. So here some remarks. Because we require locality, that's how timescale and dynamics, the notion of dynamics emerge. By these random ensembles or pseudo random ensembles at the output, we can also use them to or understand them as describing the generic or typical behaviors within the ensemble. And it gives us a certain notion of equilibrium. Okay, so these random quantum circuits are widely important in both quantum information and fundamental physics. We have a lot of technological applications like randomized benchmarking, tomography learning, error correction, etc. And in physics, it gives us a discrete model for quantum dynamics that we can use them to understand certain aspects of complex many-body dynamics and black holes, things like those. And they are very active at the frontiers of condensed matter, statistical physics, and quantum gravity. Okay, so let's get into the slightly mathematical or rigorous definitions of these elements. So to rigorously characterize unitary designs, we look at these things called the teeth moment superoperator of the ensemble E. And we say E is a exact T design if this teeth moment operator is equivalent to the Haar version of it. If you just take E as the Haar measure over the unitary group. And for this unitary group version, it's just a projector onto this convergence space. So the problem that we are interested in is the convergence efficiency or speed of the ensemble E. So what we do is we apply this ensemble E repeatedly. And mathematically, the question is what determines if this ensemble converges to designs and at what rate. So it is very easy to see that as long as this operator norm of the difference of the moment superoperators is smaller than 1, then by repeatedly acting the ensemble, this this difference will get smaller and smaller, and then this ensemble will converge. So then what quantities controls the rate of the convergence? Here, the answer is the this notion of spectral gap of the T's moment superoperator. It's 1 minus the maximum value over the second largest eigenvalue of the spectrum and the absolute value of the minimum eigenvalue. So here, this notion is very central to the whole story, and later we'll see how this happens. And then we used this same definition, the strong definition of approximate designs, introduced in the morning, this relative error version of designs. Then we can show that this spectral gap quantity will control the depths needed to generate epsilon approximate T designs. Okay, so later for the second part, we'll talk about the symmetric case. And then we have all these analogous definitions where we just replace the unitary group by a certain symmetric unitary group or commutant. Okay, so here, what do I mean by stochastic quantum circuits? So here is a quantum gate. So for normal circuits, this can mean a fixed gate. And in standard random circuit discussions, these are usually just by default chosen as hard random local gates. And here, the modification we make is that we allow this gate to be sampled from an arbitrary distribution or ensemble. Then the fundamental question are the following. First of all, do they even entangle or scramble, or do they converge? And if they do, how fast? And this will sort of signifies. Later we'll see. We'll explain more why it gives us insights about the gate efficiency and power. But here, very intuitively, it describes how fast this ensemble can help you explore the unitary group or the state space. Okay, so let's start with some very heuristic examples. So here we are considering only one qubit, and this is probably the simplest ensemble that we can think of. So this ensemble is composed of a distribution over Hadamard gate and Z phase. Okay, so this is just basic ensemble. And before we ran the result, I was expecting the behavior to be very simple, but actually when we really compute the gap behaviors of this arguably the simplest ensemble, it can actually already exhibit very complicated behaviors. For example, we are of course most concerned with the maximum value that it can take at some phase rotation angle and some distribution over these two gates. But we can see that for even t equals 2 and 3, it can show some behaviors that is just not possible to imagine a priori. So and then we can do some also do some simple addition. We consider another entangling gate, C naught now for 2 qubits, and it can also already show very complicated behaviors even at t equals 2. So this is sort of telling us that we really have to get our hands dirty to do the computation to understand the convergence behaviors. Even these very, very simple ensembles can show some behaviors that we just cannot really expect. Okay, so here there's a very simple model that we propose to consider. This thing we call it the iron gadget. So what it does, so these pink circles are hard random one qubit gate, and in the middle we put a fixed two qubit gate. So this gives us a ensemble, but obviously it's not necessarily the hard random ensemble. And why this is important, I now argue that we have multiple strong reasons. So first, experimentally, so for a long time when I was talking with experimentalists from different platforms, they always tell me that the one qubit gate is very simple and we can do it very precisely. But we want you to tell us what two qubit gate is the best. So we can, because two qubit gates are harder for us, so we can fix a target of two qubit gate and just focus on optimizing that fixed gate. Okay, so because of the difference in difficulty between single qubit and two qubit gates or entangling gates, experimentally, for example, when we were if we were trying to prepare a local random gate, we can consider these one qubit gate to be sort of free. So we can assume them to give us the ideal hard measure, which has no problem. But we want to fix some two qubit gates. So this aligns with experimental interest. And also from a mathematical perspective, say our goal is trying to evaluate or compare the efficiency of different two qubit gates. And the reasonable way to consider that is to sort of mod out all the single qubit gates. And this is the reasonable way to do it. And in the next slide, we'll see that it also aligns with a very nice mathematical tools called the KAK decomposition. So using this framework, everything come together pretty nicely. And these single qubit hard random gates will give us a projection structure that simplifies the problem. So later we'll see that under this model we can actually get a lot of results. Okay, so very briefly about KAK decomposition. It is a decomposition of any two qubit gates into this form. So these purple circles are just some single qubit gate, and in the middle we can have a three-dimensional representation of a two qubit gate. So it's sort of saying that if we want to mod out the single qubit gate, then we can use only three real parameters to describe equivalence classes of two qubit gates. Okay, so then further, so now we have a three-dimensional representation of the gates, right? And then by modding out some additional symmetries in this in these three parameters, we have this thing called the wild chamber, and we can put all equivalence classes of different two qubit gates in this chamber. And here is some illustration of where those very well-known gates sit. So C naught is here, B gate, which is best for compilation, sits in the middle, and the relatively trivial swap gate sit on the top, and we have some other gates that we'll talk about later. So here, now this is a list of common different entangling gates that I pull out from Wikipedia. And then here a motivating question that we are trying to answer is, now we have all those different choices of entangling gates, then which of them is the best? So this best, of course, has some different notions, but here, because we are looking into the design generation or convergence, we're more or less talking about a statistical notion of the power of gates. Okay, so here is the first really interesting, in my opinion, result, which is that this set of very specific three parameters, three KAK coefficients, gives us the exact solution of a second moment and third moment superoperator that has exactly the same spectrum as the Haar measure. So what this is, let me translate this a little bit. This is saying that using one single gadget. So now we have one 2-qubit fixed 2-qubit gate in the middle and single qubit hard random gates sandwiching the 2-qubit gates. Then this simple gadget already gives us exact 2 and 3 designs. Okay, so this is yeah, let me say it again. So this is one fixed entangling gate that prepares designs. So obviously it is this is optimal for local gadget auto convolution. So let's say if we want to prepare 2 and 3 designs, this is very friendly for experimentalists. And so also here, quite remarkably, we see that the randomness, like the entangling part, doesn't have any randomness. So it's sort of saying that the single qubit randomness can already supplies enough randomness for 2-qubit 2 and 3 designs. And in compilation or synthesis context, we know that, for example, the optimal gate is B, and we need 2 B gates to compose any SU4 gate. So this sort of halves the minimum entangling gate cost of Haar measure if we only need 2 or 3 designs. So yeah, this is sort of a minor point, but the B gate, so we need 2 B gates to compile any SU4 gate. Yeah, so here, but so for example, if we want to prepare Haar measure, we need at least 2, right? Yeah, but here, if we only want to prepare 2 and 3 designs, we only need one gate. Yeah. So yeah, let me also mention that. So this solution is a unique solution within the after modeling out the symmetries. So within the wild chamber, and you can see that the solution is pretty delicate. So we also anticipate this to have some number theory origin, but we haven't fully figured that out. But here for 2 and 3, the this very delicate solution of the KK coefficients gives us exact 2 and 3 designs. Okay, then it's very natural to ask, what about higher orders? And here we can actually close the question by proving that for order greater or equal to 4, it is actually impossible that this happens. So it's like for greater or equal to order 4, the single qubit randomness is not sufficient to supply enough randomness for preparing the design. So this is also a mathematically pretty elegant proof. It's just it's also very easy. So the intuition is just to count the rank of the corresponding or effective dimension of the corresponding Haar measure moment superoperator. And for T greater than 3, we can show that the effective dimension provided by the single gadget structure is not efficient. It's not sufficient, sorry. Okay, so then this is a list of those several different most important 2-qubit gates. So here I highlighted 2. So this Chi gate is this very strange solution that hasn't come up elsewhere, we think. And but the nice thing or the special thing about it is this effective spectrum is exactly 1100, which is the same as the Haar measure. So by plugging this into the definition of the spectral gap, it is exactly 1. So this already gives us exact 2 and 3. And here, let me point out another very special gate, whose importance will emerge later, which is the I swap gate. So if we just calculate the spectral gap, you see that this is just two-thirds. It's because we have to take the absolute value of the minus 1/3. So this is not, if we look at this local spectral gap, it's not as good as the Chi gate. But here, the special thing is that other than the 2 ones that we have to match the spectrum of the Haar measure, all other eigenvalues are negative. So this is a very special thing that will show its power later. And maybe more familiar to physicists, this I swap gate, a special property of it is a so-called dual unitary gate. And also B and C naught are also dual unitary gate. So let me leave it here, and later we'll comment on that again. Okay, now so far we have only talk about local convergence. So what about the more important scenario of many-body circuits? So here we consider this very simple model, which we call graph circuit model. So we just sample an edge from the graph that describes the connectivity of or geometry of the architecture that we are considering. So for example, they can just be one-dimensional lines, or higher dimensional lattices, or some other topologies like cycles or stars, or complete graph, which is also very important. And then we first sample an edge according to the graph, and then we apply our ensemble on each edge. Very natural definition. So now in this many-body circuit, the global ensemble will look like this. Still, these U are fixed 2 qubit gates, and these pink circles are single qubit Haar random gate. And then the definitions just get modified, and this is the many-body moment operator that we will. So in order to consider or analyze the convergence properties or efficiency, we are looking at this many-body version of the moment operator. Okay, so here a very important phenomena is that. So let me first give a little bit of intuition what is happening. So when we consider the many-body version, the small eigenvalue will get lifted after we repeatedly apply the ensemble, and very intuitively, if the eigenvalues are really small, it gets lifted somewhat slower. And so at some point, so for sufficiently large n, so here we give a condition on the n, but you can just take it as sufficiently large now. So for sufficiently large n, even for the spectrum like I swap, which had purely negative eigenvalues outside of other than 1, the eigenvalues will get bigger and bigger because of the convolution. And then the second largest eigenvalue will eventually become greater than 0. So here what happens is that we can show that there exists some value such that as long as n is greater than this value, then the spectral gap of this many-body ensemble will be purely controlled by the second eigenvalue instead of the minimum the absolute value of the minimum eigenvalue. Okay, then so here we have a series of different mathematical approaches for proving and comparing the many-body moment operator gap. So the first very straightforward one is directly just comparing the difference of the two moment operators and proving a ordering by positive semi-definiteness. So by this very straightforward approach, what we can prove is that the I-swap gate for sufficiently large n and under this little bit complicated condition, it's always the best gate, or no other gate can outperform the I swap gate on any graph. So here for technical reasons, we have to work under this condition. But if we look at what it does in the wild chamber, it just takes out a small portion that's around the swap gate, which we know is trivial, right? The swap gate doesn't entangle. And so actually, very interestingly, although we take out a portion, and that portion is supposed to be trivial. So here we're actually conjecturing that the I swap gate is absolutely the best, but it's just for the technical limitations of our current method. It just doesn't really work. So the applicability region is actually the orange one. Yeah. But those gates are this region contains all the non-trivial gates that we saw. Okay, now let's look at this I swap gate again. All right. So as mentioned, the spectrum has a very special structure, which is other than the ones, other eigenvalues are purely negative. So locally, if we look at the local gap, it's just 2/3. So it's not really random, right? But by the suppression theorem that we had a few slides ago, we know that in the many-body regime, these negative eigenvalues will show power because they get lifted a little bit slower. So what happens is that although this kind of gadget is locally less random, but global randomness can emerge faster. Okay, so this is a very interesting phenomena that should have some fundamental that should provide some fundamental insights into this random circuit business. So if we let's say if we are now doing the random circuits with local hard gates as we standardly do, then this local hard gate circuit will actually generate design slower than this. Right now, so maybe let me show some examples here. So this chi gate is just the gap of the local hard gates. So the bolder ones are the largest gap in this category, and we can see that the hard gate is always not the best. Okay, so yeah, I went a bit too fast. Let me get back a little bit. So this is another different approach for comparing the gaps between different iron circuits. So this is also a widely used method in representation theory based on the so-called Dirichlet forms. And when we apply this approach, it involves some Markovianization procedure. But then, so the point is, it gives us a different method for doing this spectral gap comparison or analysis. But for this particular problem, for the many-body graph circuit problems, it gives us the completely equivalent result as the approach one, the positive semi-definite ordering approach. And then we also have yet another different approach based on some relatively heavy manipulation with representation theory techniques. And here, the new result that we can get from this approach is what we call the absolute optimality of the I swap plus complete graph circuit. So here, what we can prove is that for n greater or equal to 3, the combination, the dual of I-swap plus complete graph is like no other gadget can outperform this combination. Okay, so it's like the intuitive message is sort of like whenever it's possible for you to do I-swap gate and a connectivity given by the complete graph with no other geometric constraint, then you should just always use this combination to do your random circuits. It gives you the fastest convergence to designs. Yeah, so this is the table I showed just now. So as I said, the bolded numbers are the largest gap values, which indicate the fastest convergence for for a few different sizes of the system and different graph topologies, and these are the different gates. So some messages that we can get from this numerics is that indeed for all cases, so the previous results are like for sufficiently large n, but actually if we look at these small sizes, then iSwap is still always the best among at least all these examples that we try. But on the other hand, the B gate is pretty good too. And here, especially for complete graph, you can see that the iSwap, C naught, and B for relatively larger sizes, they all give the best gap. And what's their a common property? They're all dual unitary gates. So this will lead us to another conjecture that we'll make later. But here the point is that the iSwap gate is really good, and B gate are usually pretty good. And in response to John Yang's question, so the last column is the gap given by a local exact 2 or 3 designs given by the Chi gates, right? But we see that among all these examples, they are always smaller than some other choices. So that's what I mean by the local hard random gates actually give rise to slower convergence in a global sense. And another tricky thing is that the ranking of the gates actually depends heavily on the specific parameters or graph topology that we choose. So let's say if we work with a specific size or graph, we really need to do the numerics to, yeah.
So for R random, the complete graph, even C naught is better than R.
The C naught gadget, yeah. So, well, I do not have very insightful answers, but yeah, so the dual unitary gates tend to perform really good on complete graphs. That's what we observe. But yeah, that's maybe one thing that I'm looking for physical intuitions or yeah, same class. Okay. Yeah, well, C naught and CD are even stronger. They are KK equivalent. Yeah. Okay, thank you. Maybe I can ask you later. Yeah. Okay, so we also have some results about some other possible or natural circuit architectures, but here I will not go too deep into them. So yeah, so what one point is that ISWAP still looks to be very good even for these slightly different architectures, which might not be so surprising, but that's the observation. Okay, so here let me give you some conjectures that I consider to be sort of interesting or maybe feasible for you. So first, as I said, we of course we want to really prove under like no assumptions that the iSwap gate is the best gate for many-body convergence. And the second, I also mentioned, we conjecture that for sufficiently large n, all the dual unitary gates or the combination of dual unitary gate and complete graphs also give the same best efficiency as the ISWAP gate. So at least that's what we observe from a bunch of numerics, but it's not yet clear to us how to prove that. Yeah, and then the last one is the brickwork model that has been studied the most. We also conjecture that the ISWAP gate for a large enough n will be the best. Okay, so let's do a small awarding ceremony for all these different 2-qubit gates that we mentioned. Let me be relatively quick. So this chi gate is a new gate with these very delicate coefficients that we found. So the KK coefficients is quite close to B, but also because of these R cosine 1/5 things like those, we know it's not B, and it definitely shows up for some deeper mathematical reasons that we seek to understand. And then if we look at the local convergence, it gives us a unique exact solution for 2 and 3 designs. So it locally looks exactly like her. But when we increase the system size and look at the many-body version of the convergence, it starts to become suboptimal. And for the many-body case, what emerges to be the champion is the I-swap gate. And from if we look at the spectrum, other than ones, they have a purely negative eigenvalues, and we have explanations why this helps convergence. And for most many-body cases, we believe that the ISWAP gate will give us the best efficiency. And then we have some other gates. The B gate is known to be the best for the compilation task, and for the convergence setting that we are looking at, it's also pretty good. And together with C naught, they are dual unitary gates that we expect to also be the best for with complete graphs. And then we also have all these other very well-known 2-qubit gates, especially square root ISWAP gate and the QFT gates. They are known to be important or very fan favorite in some other scenarios, like certain experimental platform implementation or parameterized circuit in terms of things like quantum Fisher information and some algorithms. They are the most liked 2-qubit gates. But here we see that their convergence efficiency is actually not so good.
Some sort of that double pair starting from product state, then do they perform all equally on the complete graph?
No. Yeah. So here are some. So other than these, the square root ISWAP QFT gates, they're all entangling gates. Oh, maybe you're talking about maximally entangling gates. I need to think more about that. Maybe let's chat offline. Yeah. Where was I at? Okay. So of course in practice, like the implementation is never exact. So we also need some robustness or continuity guarantees. So this is a high level description of the result. So yeah, of course the 182 is not given here, but just trust me, it is a very natural definition of the perturbation size. And what we can show is that the variance on the gap will be at the same order of the perturbation. So we have a pretty good robustness or continuity properties of these convergence efficiency analysis. Yeah, I'll just skip this. So here we just do a perturbation numerics, and so So if you look into the details, what you can get from these graphs is that they look pretty continuous. Okay, so then it's also very natural to consider higher locality gates or hypergraph circuits. So one almost mathematically trivial bound is this one obtained from the Wiles inequality, but it can give us some useful guarantees, which is that as long as we are considering O1 locality, then the gap always scales better than 1 over n, which gives us the same efficiency. And then because of the lack of very clean decomposition like KAK for 3 qubit gates and above, we do not have a very systematic approach for analyzing or comparing the different higher locality gates. But we did some numerics on these most well-known gates, and it turns out that the so-called Margolis gates seems to be the best, at least among these examples. Okay, I really want to talk about something about symmetry. So this iron circuit is just, of course, one special setting of the stochastic quantum circuits, and another very naturally motivated model is the Clifford plus magic models. And here we are considering this analog of the iron circuit model. And let me just show a few results. So of course here, because the multi-qubit Clifford group already gives us exact 3 designs. So our target is to prepare higher order designs. And if we consider this Z phase gate as the thing that's added to the Clifford gates, the gap for higher order T will be analytically given by this. And we can see that indeed the most magical phase gate among this Z phase family indeed gives us the optimal convergence. But then if we consider a general one qubit gate, we can also analytically solve the convergence, for example, for the gap, for example, for order 4. And then we have so this square root 3, 1 over square root 3 thing is the so-called phase gate that's supposed to be most magical among all single qubit gate. But we also have other solutions. Okay, so here is like the amount of magic is not the only thing that controls the convergence efficiency for the Clifford plus magic model. Okay, then so here I'll try to cover the second part, the symmetric unitary, rather quickly. So here the question becomes, so the general framework is that before we were considering notions like designs over the unitary group, right? Here we can consider the notion over other groups, and for physical motivations, here we consider 2 typical examples, which are the U1 symmetry and SAT symmetry. They are respectively abelian and non-abelian continuous symmetries. And for this case, it's very natural to expect that the Schur-Weyl duality will give us connection to the symmetric group representation theory that will be heavily useful in the analysis. Okay, then for this case, the definition of symmetric unitary is just given by this covariance property with respect to the representation that we are considering about these groups. Okay, yeah, here, let me mention that here we are considering the tensor product representation, or for physicists, maybe like on-site representation, or for quantum computing people, the transversal representation of these different symmetries. Okay, so yeah, so this is the definition of symmetric unitary, and all those relevant definitions, we just need to replace the entire unitary group by the symmetric subgroup. Okay, so here is a demonstration of the restrictions on the structure of symmetric unitaries. So here for the U1 symmetry, it's very natural to imagine that we now have now the symmetric unitary has to take this block diagonal form. Each of them correspond to a charge sector, and if we consider more complicated SU2 symmetry, it actually gives us more constraints. And actually, without using too much mathematical jargon, the sizes and the number of these small blocks will actually be very key to the analysis. Yeah. So here I try to summarize the important things or properties of these scenarios in this table. So first of all, we already know from simple Lie algebra counting arguments that under continuous symmetries, we even cannot have universality with local gates. Okay, so here pretty much every item is one or even more papers. So of course here I don't have enough space to list all the references, but if you're interested, I have some other slides. So we know that under these local symmetries, we do not even have universality, and if we relax the universality requirement a little bit by this thing that's sometimes called the semi-universality or universality without relative phases between different charge sectors, then we have these locality requirements for different symmetries, which actually require some effort to prove. And then if we want exact designs, we have discrete gate families for the symmetry-free case. But here for U1 and the SCD symmetry, only continuous gate families are known. And then we are also we're most interested in the convergence or generation of approximate designs. Then here the most important feature is that with fixed locality gates, from universality arguments, we already know that we cannot expect to prepare the Hart measure, right, or arbitrarily high order designs. So here, what can also be shown is that with fixed locality, we can only prepare polynomially high order approximate designs, and the technical results on the main result of the paper that I listed in the title of the talk is to prove that to give a concrete construction of a U1 and SUD symmetric local circuits that can provably converge to design in polynomial time. But this polynomial is actually worse than the polynomial in the symmetry-free case. And this is very important because this is related to, so although we are just adding, it seems that we are just considering the analogous version with symmetries. Actually, mathematically, everything becomes very different. Okay, so these are some of the known methods for proving the convergence rate in the symmetry free case. So they're all very well studied and give rise to a series of nice improvements on the gap scaling. But here, the point is that for the symmetric case, they all fail to some extent. So here, the mathematical and some physical explanations can be found in these other papers. But here, the take-home message is just that for the purpose of proving convergence efficiency under symmetries, these previously known method just magically breaks down. And there are some other methods or technique elements, I would say, that's also not very feasible in this context. So here is sort of a demonstration of the fundamental difference or challenges that we have to get around if we want to approve convergence, rigorous convergence guarantees for symmetric circuits. Okay, then here is our proposed solution. So this Yeah, so this name, let's not worry too much about this CQA name. It has some representation theory background, but here it's just the ensemble definition for the U1 and SUD cases respectively. And very informally speaking, our the result that we prove is that these CQA ensemble, they are symmetric and they are local ensembles, right? And what we prove is that they can converge to a symmetric tube designs in polynomial time or efficiently. And this requires a completely new approaches because basically all the known ones are not really useful here. So here is a very brief illustration. Yeah, so without all the definitions, of course, it's not so informative, but let's just say that it's a combination of advanced techniques from representation theory, graph theory, and Markov chain theory. And we can see that some elements we have overlap with the first part of the talk, like comparison with via Dirichlet form and some other representation theory manipulations. But the point here is that we really have to devise new methods in order to overcome the fundamental barriers or fundamental limitations of known efficiency methods. Okay, so why do we care about these things? So here are some examples of applications for insights. So first, it is conjectured in this earlier paper that we can have local symmetric circuits that efficiently generate the near optimal covariant quantum error correcting codes. And here maybe one particularly interesting case is the SUD covariant codes, because these codes are codes with transversal universal logical gates. But you might say that it is contradictory to the Easton-Kneel theorem. So this is actually a approximate code. Okay, so here it's like we have this code with transversal universal gates, so it's better in terms of fault tolerance on this aspect, but it's not a exact code. So it will be very interesting to investigate these kind of trade-offs in fault tolerance implementation. And then with this kind of circuits, very similar to why we like to play with random circuits for these physical reasons. This also gives us a playground for understanding the physics of scrambling under conservation laws. So in this paper, we discuss some special behaviors under symmetries. For example, like the residual conserved quantities or OTOC, they have different scaling than the symmetry-free case, and we can also, of course, play with them to understand the modified or the different decoupling and entanglement properties and information dynamics. And we also have some other technological applications in the context of things like geometric quantum machine learning and parameterized circuits. Here, let me throw a stone, something that I wanted to understand, but because here we only prove efficient convergence to two designs, so we cannot use the design-based arguments for complexity yet. So here, it will be interesting to understand the circuit complexity dynamics under conservation laws to understand things like whether they still grow linearly. Okay, so yeah, I'm a little bit over time, so this is a summary and outlook from these two different. So we consider the convergence or design generation problem in these two different circuit settings: the stochastic quantum circuit and symmetric quantum circuit. And maybe one thing I want to highlight is that from these settings, we have a lot of very interesting mathematical problems that we had a lot of both fun and pain working with, but we believe they can eventually give us some really nice mathematical or and physical insights. And then we expect it to be interesting to extend some of the results to more general settings, including QIDs, continuous variable, and higher designs. And some of them are obviously actually very non-trivial. And we would like to know more about the applications and the in relation to experimental implementation, or what experimentalists have to say about these results. Okay, so I think that's it. Thank you. Okay, so these three methods, they can only give us constant gap, like in some normalized sense. So, but for the symmetry case, so we have physical reasons, things like diffusive transport, ghost modes, and stuff, to and that also happens in our proof, that we actually have polynomially slower convergence. So these methods are not useful for giving us bounds.
I think recently Zhongwan had a pretty on this.
Yeah, I think Tommy mentioned that in the morning, but I haven't really read that in detail. Yeah.
I think from the diffusive node, which is also
So I'm basically saying that that gives lower bound, right? Yeah. So the point here is upper bound. Yeah. But the upper bound is polynomially slower than that. Yeah.
This is happening for any one. This is always happening, like the difficulty of these forces not working, or is it?
So for continuous symmetries, yes. Yeah.
I think for continuously, it already happens that just a density of charge has to diffuse.
Yeah. Yeah.
At the higher design.
Yes.
Is there like one special property of the equals to allows you to get the extremes elsewhere that doesn't make sense?
Oh, so at least our approach or the techniques that we develop for this CQA ensemble, it's impossible to work for 3 and above. Yeah. Yeah, the like the dimension counting and stuff becomes intractable. So magically we can only prove 2 design here, but this says nothing about whether you can prove higher designs using other circuit ensembles.
Thanks,
Thank you so much.